Many of our lecturers have received Excellence in Teaching awards, are recognized internationally, and are rich in practical experience. Students have access to excellent facilities that rank amongst the best in the world. 300 million rands has recently been invested in new teaching and research facilities, state-of-the-art laboratories, and improved equipment. The 30 million rands new School of Engineering building is the envy of engineering campuses across the country.
Okay, good evening, everyone. Thank you for joining us for this final revision session. Today, I want to start by going through some questions that students have emailed me. And then when we're done with that, I've chosen a few more examples from past your exam papers. Okay, so as we go through the solutions, if you have any questions, then you can just stop and ask me and I'll answer it for you. Okay, so students have asked me to please do questions on momentum, on Newton's laws, and electrostatics and electricity. So I want to do those questions first. Okay, so I want to start with this question. That's question 2 from the June 2021 paper that you've written. Okay, so an 8 kg block on a rough horizontal surface is connected to a 2 kg block by a light inextensible string passing over a frictionless pulley as shown below. The 8 kg block moves at a constant speed. Okay, so they're telling us it's not accelerating. When pulled by a 29.6 Newton horizontal force to the right, the frictional force acting on the 8 kg block is 10 Newtons. Okay, so this is the diagram for us. And and I just want to say, when we're going through in today's session, I'm not going to go through all these, all the theory definitions and stuff, because you already did it. We're going to go through all the calculations today. Okay, so question 2.2 says, draw a labeled free body diagram for the 8 kg block. Okay, so if we look at the 8 kg block, then we need to draw all the forces that are acting on the block. Okay, I'm going to, sorry. Let's just do this. So, sorry, when we're drawing the free body diagram, we just draw the object as a dot or a small square. So for the 8 kg block, it will have its weight acting downwards, which you can label as weight, or you can label it as mg. It is resting on the surface, so it will have a force that is perpendicular to the surface called the normal force. We are told that it's being pulled by a force F to the right. And we know that it's connected to the string. So there is a tension force to the left. And we know that there is a frictional force as well. Okay, so that is the free body diagram of the for the 8 kg mass. Okay. Question 2.3 says, calculate the tension in the string. Okay. So if we look at this block here now, we've already drawn the free body diagram. We know that the frictional force is 10 Newtons and the applied force is 29.6. So we can calculate what the tension force is. So that's what we're going to do now. sorry. Okay, so 2.3. So we start off by saying that the net force is equal to mass times acceleration. And what are the forces that are acting? So we know that it's, and I'm taking to the right to be positive. So I'm going to have F minus the tension minus the friction is equal to mass times acceleration. And the acceleration is 0 because it's moving at a constant speed. So that's equal to 0. So the force is 29.6 newtons minus the tension, which we are trying to calculate, minus the frictional force, which was given to us, is equal to 0. Okay, so here we can just see that the tension force is just equal to 29.6 minus 10, which is 19.6 newtons. Okay, so that's the first part. Now the next part says the 29.6 Newton horizontal force is now increased to 50 newtons. Okay, so when the force was 29.6 newtons, the block was moving at a constant speed. When you increase that force, then the block's going to accelerate. But they tell us now, apply Newton's second law to each block and calculate the magnitude and acceleration of the 8 kg block. Okay, so now the force is 50 newtons. Okay, let's do that. So 2.4.1. We start off with our Newton's equation again, that the net force is equal to mass times acceleration. And the forces are still F minus T minus the frictional force is equal to mass times acceleration. Okay, the force is now 50 newtons minus T, we don't know what it is, minus the frictional force, which is 10 newtons. And that is equal to, the mass is 8 kgs. And we're trying to calculate the acceleration. So 50 minus 10 is just 40, minus T is equal to 8A. And so we will just call that equation 1. Okay, and remember we're taking to the right to be positive. So that's for the 8 kg block. Now we must apply this Newton's second law to the 2 kg block. So let's do the same thing, and you can do it with me. We start off by writing F net is equal to MA. And in this, for the 2 kg block, I'm going to take upwards to be positive. If I take upwards to be positive, then my tension is going to be positive. The weight's going to be negative, and that's going to equal to MA. So it's T minus, the mass is 2 kilograms, G is 9.8. And 2A. So you'll get T minus 19.6 is equal to 2A. And you can call this equation 2. Okay, so we have equation 1 with T and A as unknowns. We have equation 2 with T and A as unknown. we have two equations with two unknowns, so we can solve them. And if we look here, you've got minus t in equation 1, and you've got plus t in equation 2. So we could just add equation 1 plus equation 2. Okay. And then if you do that, you will get 40 minus 19.6 is equal to 10a. Okay, so 20.4 is equal to 10a, and you can solve this whichever way works for you. A is equal to 2.04 meters per second squared. And that is how we find the acceleration of the block. Okay. So that's 2.4.1, the magnitude of the acceleration of the 8 kg block. And now we want to know, what is the tension in the string? Okay, what is the tension in the string? You have equation 2 and you also have equation 1. So now all you have to do is substitute this value for acceleration into whichever equation you want. Okay, both the equations are easy, so you could choose any one. We will just choose t is equal to 40 minus 8a. So that is equal to 40 minus 8 into 2.04. And you get 23.6 newtons. Okay. And that is how we answer this question, or these type of questions using Newton's laws. Okay, so F is equal to ma. If it's constant speed, we know that the acceleration is 0. So that's what we did there. And if we have the acceleration, we can write out two equations, one for each block, and then solve whichever way is convenient. Okay, do you have any questions on this part? Okay, if not, then I'm just going to move on to the next question, which is question 7. Okay, so here's a question on electrostatics. Two charged spheres, R and S, are both stationary on a smooth insulated surface, inclined at an angle of 25 degrees to the horizontal. Sphere S of mass 0.01 kg and carrying a charge of minus 6 times 10 to the minus 9 coulomb is connected to a 0.03 meter long light inextensible string attached to point P at the top of the incline. Sphere R carrying a charge of plus 5 times 10 to the minus 9 coulombs is held such that the distance between the centers of the sphere is R, as shown in the diagram. Ignore the effects of friction. Okay, so they've given us the angle, the inclination here, and they've given us the charges. Okay, so sphere R exerts an electrostatic force of magnitude 1.2 times 10 to the minus 3 newtons on sphere S. 7.1 says, state Coulomb's law in words. Okay, you can do that part. 7.2 says, calculate the distance R between the spheres. Okay, and it's with 3 marks. So when we do these type of questions on electrostatics, they can give us both the charges and the distance between them and ask us to calculate the force, as we've done in a previous example. In this question, they're giving us both the charges and they're telling us what the force is. They're asking us to find the distance, okay? The distance between the spheres. So all we have to do now is rearrange the Coulomb's equation. Okay, so let's do that. Okay, so it's question 7.2. So we know that the force is equal to 1.2 times 10 to the minus 3 newtons. And I know that Q1 is, Q is 6 times 10 to the minus 9 coulombs, and Q2 is 5 times 10 to the minus 9. Okay, and remember when we put the values into this equation, we do not put the negative signs. So the equation is F is equal to K Q1 Q2 over R squared. Okay, and we are trying to find R, so I prefer to write it as R squared is equal to K Q1 Q2 divided by F. Okay, and then once you get to this stage, the rest of it is to put in the values and get your final answer. Okay, so K is 9 times 10 to the 9, 6 times 10 to the minus 9, 5 times 10 to the minus 9, divided by 1.2 times 10 to the minus 3. Okay, when I did that, got 2.25 times 10 to the minus 4. And so that's R squared. So then R was just equal to the square root of that. Okay, so maybe again, I'm writing too many steps just to show you what we've done. You don't have to write as many. Okay, and you get 0.015 meters. Okay, so that is the value of R, the distance between the two spheres. Okay. So the next question is, draw a labeled free body diagram for sphere S. Okay, so if we look at sphere S, remember what they said? They said two charged spheres are both stationary on a smooth insulated surface. So S is resting on a surface. So whenever we have this charge, we know we're going to have some weight acting vertically downwards. It's resting on a surface, so we're going to have a normal force perpendicular to the surface. And then you've got this string, which is attached to point P that is holding it, so there's a tension pulling up. And then you have a charge R on the other side, which is going to be attracting S. Okay, so let's draw they said a labeled free body diagram for charge S. Okay. So if we draw this dot to represent S, then in the direction there, that is the tension, okay, of the string. Vertically down is the weight, or we can call it mg. Perpendicular to the surface is the normal force. Okay, and then there is the electrostatic force F there. Okay, so that is the free body diagram for sphere S. Okay, so we draw the body and we draw all the forces that are acting on it. Okay. Okay, draw the free label the free body diagram. And now they want us to calculate the tension in the string. Okay, calculate the tension in the string. So when we're going to do that now, we'll look at our free body diagram. And these charges are stationary. So again, we're going to, let's do this. We need that drawing. Okay, 7.4.1. So we start off by saying that the net force, okay, we can write the sum of the forces, or you can say the net force. So let's just stick to the net force is equal to MA, which is equal to 0, okay, because they are stationary. Okay, so now we're trying to find the tension. So we're going to choose, or we're going to work along this direction. Okay. Okay, so if we are looking now, we're trying to find the tension. Okay, let me just do this because I'm sure you know it, but we will now have to get the components of the weight. Okay, so one will be perpendicular to the surface and the other will be parallel. Okay, so the one we're going to be interested in is that component, the mg sine of 25 degrees. Okay. Okay, so now we're writing out our equations. Let's add up all the forces in the direction of the tension force. Okay, so this mg force is acting in the opposite direction. So it's going to be minus mg sine of 25 degrees. Plus the tension force minus the electric force will equal to 0. Okay, and so we can rewrite this. We're trying to find the tension. So I can just write it as the tension is equal to Fe plus mg sine of 25. Okay, and that is 1.2 times 10 to the minus 3 plus the mass is 0.01 kilograms. G is 9.8 sine of 25. And if you do that, you should get 0.04 newtons. Okay. So I'm just pausing for any questions or. Okay, so.
I think there is a question here.
Okay.
It's saying, are we not using W parallel, which is mg cos 25?
Okay, wait. Okay.
So the question is, are we not using weight parallel, which is mg cos 25?
Okay, maybe I must just let me just quickly explain to them when it's cos or sine.
Okay,
Might be worth do that now.
Okay, thanks.
Okay, so thank you. So let's draw the incline here. And we know that this is 25 degrees. And then we have the weight acting down like that. Okay. And I'm going to continue this line here. Then we have the normal. That's 90 degrees. Okay, and that is also 90 degrees. And if we had to continue this here, with the weight coming all the way down here, then that's also 90 degrees. Okay, let me just neaten this up. Okay, so I just take this along and let's just make this line come down here. Okay, I brought it down there so that you can see that that's 90 degrees there. So the components that we are talking about, and I will have to use a different color, it is the one that is here, which is the parallel component. You can see it's the same direction as that line there to the surface, or it's the one that is here, which is perpendicular to the surface. Okay, so this is the parallel one. The one that we're talking about is this one here. Now, how do you know if that is mg sine theta or mg cos theta? Well, I'm saying to you that if this angle here is 25 degrees, then this angle here is 25 degrees also. And if this angle is 25 degrees, then this side here is mg sine of 25. It's not mg cos of 25. Okay. So this component here is a mg sine component. It's not a cos component. Cos component here is the one that's perpendicular. Okay, I hope that answers the question.
Yeah, I hope so too. I think so. Thank you.
Okay. Okay, so that's finding the tension. And then the next question is asking us to find the net electric field at point P. Okay, so we've done this previously. Maybe I'll just briefly go through this one again. It carries 5 marks because remember, to find the net electric field at P, you have to find the field at P due to S, and then you must find the field at P due to R, and then find the resultant field. Okay, so when we're doing that, remember, we need to know what the distance is from the charge to point P. So if we look here, S to P is 0.03 meters. And from R to P, it's 0.03 plus R. Okay, so when we're finding the distance from here, that is R plus 0. R plus 0.03. Okay, so I'm just telling you, reminding you of this because we're going to use that in our calculation now. Okay, so let's find the net electric field at point P. Okay, so 7.4.2. Okay, so the electric field due to R at P is equal to KQ over R squared. Okay, and then that's going to be 9 times 10 to the 9, and Q is 5 times 10 to the minus 9, divided by, and now this is the important part, okay? It's 0.03 plus, and R we have calculated already. So let's go up. Here's it here. This is the first one. They asked us to calculate the distance R between the two, 0.015. So it's 0.015 squared. Okay, so when you put that into your calculator, you get 22,222.22. I kid you not. Okay, Newton per Coulomb. Okay, what's the direction of the electric field at P due to R? So let's go quickly here. So at P due to R is a positive charge. If R is a positive charge, then the electric field at P is going to be that way. So you can call it upwards or to the right. I'm just going to call it to the right, okay? And now you do the same thing for the other charge. So the electric field due to S at P is equal to, and just repeat it, K Q over R squared, 9 times 10 to the 9, and Q is 6 times 10 to the minus 9. And the distance from from S to P is 0.03 squared. And if you put that into your calculator, you get 60,000 Newton per Coulomb to the left or to the bottom, okay? And so then you now can find the resultant. You just add them up. One will be positive and one will be negative. And so then you can just get that the net electric field is equal to, and you get minus 37,777.78 Newton per Coulomb, and it is to the left. Okay. I think that by now, as long as you know the method, and the important thing here is what is the distance R, so that your calculations are correct. Okay, do you have any question here? Okay. Okay, so that's 18 marks for this question. The next one that I want to do is question 8, because there've been a few questions or requests to do electricity. Okay, so we've got 3 resistors connected to a battery with an unknown EMF and an unknown internal resistance R as shown. Ignore the resistance of the connecting wires. Okay, so if we look here, you can see that we have 1, 2, 3 resistors. The 4 ohm and the 3 ohm are connected in series with each other, and they are in parallel with the 7 ohm. You've got to switch S here. Okay, the first question is a theory question. Oops. In the definition of the EMF of a battery, given below, A and B represent missing words or phrases. The EMF of the battery is the maximum electrical energy for the work supplied by a battery per unit charge passing through it. Okay, so just want to remind you that the EMF is what energy the battery is providing. Okay, the EMF does not depend on the rest of the circuit. It just comes from the battery. Okay, so with switch S closed, the voltmeter reads 2.63 volts. Calculate the equivalent external resistance of the circuit. Okay, so they're always going to ask us that, and you must get it right. So calculate the equivalent external resistance. So we're not worried about little r inside the battery. Okay, so we're going to do it by looking here at 4 ohm and 3 ohm in series. So that's just add them up. And then you've got 7 ohm in series with 7 ohm to calculate what the equivalent parallel combination is. Okay, so let's do that. 8.2. Okay, so for 8.2, I'm just going to draw it like this too. It's only a part of the circuit, right? You've got 4 ohms and you've got 3 ohms. So instead of those two, I can just say R is equal to, because they're in series, 4 plus 3 is equal to 7 ohms. So now I can redraw my circuit for just the resistors. So that's the 7 ohm that's in there. And this is the one that we just did now. Okay, I'm not drawing the rest of the circuit. So how do we find the equivalent resistance now? 1 over R parallel is equal to 1 over 7 plus 1 over 7. And
Actually,
what's 1 over? Yes?
is there a part A and a part B of the question? I think people are asking what is the answer to part A and B. Which one are those?
Oh, this is the theory question. Is that what they're asking for in your book?
I think so. Because they're asking what is part A and B's answers.
Oh, okay. Okay, guys, but you're writing your paper tomorrow. You should know the theory bits, eh? But the EMF of the battery is the maximum. So A is electric energy, or you could say work. Okay, both of those answers would be acceptable. So that's the answer for A. Supplied by a battery per unit charge will be passing through it. Okay, so A would be electric energy, or you could say work. And for B, you must say it would be unit charge, or you could say coulomb. Okay, both those answers would be acceptable. Okay, so that's 8.1.
Thank you, thank you.
Okay, so now we're trying to find the equivalent resistance in the equivalent external resistance. Okay, so I'm assuming that everyone's with us to this stage here. The two in series, 4 ohm plus 3 ohm is 7 ohm. Then you've got 7 ohm in parallel with 7 ohms, and we're trying to find the resultant. So you've got 1 over 7 plus 1 over 7 is equal to 2 over 7. So then R parallel is equal to 7 over 2, which is just 3.5 ohms. Okay, so that is the equivalent external resistance in the circuit. Okay. Okay, so that's important now. We've just calculated it to be 3.5 ohms. Okay. Okay, so now comes a very important question. Well, I think it's very important because it carries 8 marks. Okay, which means that there are many steps to follow. Okay, so the question is, or it tells us, switch S is now opened and the voltmeter reads 2.8 volts. Okay, so let me just clean this up and highlight some important parts for us. Oops. Okay, so they told us this part here. When S is closed, the voltmeter reads 2.63 volts. Okay, and then we calculated the external resistance. Now they say when S is opened, the voltmeter reads 2.8 volts. Okay, and they want us to calculate the internal resistance of the battery. So we need to go back up to this drawing and look at where S is in the circuit and what happens now when S is closed. So when S is closed, the circuit looks as it is in the drawing, where all three resistors are connected in the circuit. Okay, if we open switch S, if the switch is opened, then what's different in here? Then when this switch is opened, no current flows through the bottom resistor. Okay, so if the switch is opened, then the bottom part of the circuit, so I'm just gonna do that, all of that is not part of the circuit if S is opened. Okay, let me just remove all of that nonsense. Okay, so now you understand what's happening. Let's solve this. Okay, so S is closed. The reading is 2.63, or we also needed to see. You can see where the voltmeter is. It is only reading across the battery there. Okay, so when S is closed, the voltmeter reads 2.63. And when S is opened, it reads 2.8. Is there a question? Okay.
No, there is no question. You can continue.
Okay, so for this part now, let's just do it step by step and show you all the calculations, okay? So we're going to do the calculation. We're going to calculate when S is closed, and we're also going to do a calculation when S is opened. But what's important here is for you to realize that when we're going to find this EMF of the battery, it's not going to change depending on whether the switch is open or closed, okay? So let's do this. 8.3.1. Okay. So 8.3.1. I'm going to divide my page here for when the switch is open.
Hello.
Yes.
I'm sorry, ma'am. I didn't quite understand the question. Can you please repeat?
Yes, of course.
Thank you.
Okay. Okay, so the question we're trying to answer now is 8.3.1, which wants us to calculate the internal resistance of the battery. Okay, but before we get there, they told us some important information. They initially told us that when the switch S is closed, here, when S is closed, then the voltmeter reads 2.63 volts. Okay, so that's the information they're giving to us. So when S is closed, and if we look up at the circuit diagram here, when S is closed, the circuit is as we can see it here. All three resistors are connected in the circuit, and they want us to find the internal resistance R. But they also give us more information. They tell us that when the switch S is opened, the voltmeter reads 2.8 volts. So if we go up here and look here, when this switch is opened, it means that this 7 ohm resistor is not a part of the circuit. If the switch is open, no current flows in this bits here. Okay. So now what we're trying to do is, with the information they gave us, they want us to find what is this R here. This is what they want us to find. Okay, so that's what we're trying to do now. We want to find the internal resistance of the battery. And I'm just making you aware, it's the internal resistance of the battery, and it carries 8 marks. Okay, so the way to do it is like this. We've got a situation, or one set of equations for when the switch is opened, and another one for when the switch is closed. Okay, so when the switch is open, then what is the current that's flowing through? So I is equal to V over R. I'm going to do the equation on both sides as we go along so that you can clearly see what the difference is between the switch open and the switch closed, okay? So I'm trying to find the current, which is V over R. So when the switch is open, and I'm gonna have to go back to the drawing to show you. Oops. When the switch is opened here, then what is the resistance in the circuit? Well, when the switch is opened, there's only the 4 ohm and the 3 ohm in series with each other. Okay, and so the resistance is 7 ohms and V is 2.8. Okay, so that's what I'm going to use. When the switch is opened, V is 2.8 volts, and the resistance in the circuit is 7 because it is the 3 ohm and the 4 ohm. Put that into your calculator and you should get 0.4 amps. Okay, and if I do the same equation on this side now, when the switch is closed, what is it? So now I must come back here to show you. When the switch is closed, the voltmeter reads 2.63. And also, when the switch is closed, what is the resistance? It's all 3. And that is what we calculated in 8.2, equivalent resistance. Okay, so that's what I'm going to do now. Let's bring my page down. There's it here, 3.5. Okay, this 3.5 is the resistance. Oops. So V is 2.63 and the resistance is 3.5, which we calculated. And you get 0.75 amps. Okay, so that's the first bit, is calculating the current. Now the next bit, remember, we're trying to find the internal resistance. So the equation we use is the EMF is equal to I, external resistance plus internal resistance. And we'll do it for both sides or for both situations. I into okay. And so just put in the values here because we do not know what the EMF is. We just calculated the current to be 0.4. What is R? It's just 7. It's only the 4 ohm and the 3 ohm plus R. Okay, and we leave it like that because we don't know anymore. On this side, we just calculated the current to be 0.75. The external resistance is 3.5 plus R. Okay, now when we have these two equations, one is for switch open and one is for switch closed, there are two equations for the EMF, but it's the same battery, so it is the same EMF. So we can just equate these two equations, okay? So then I can just write here now that 0.4 into 7 plus R is equal to 0.75 into 3.5 plus R. Okay, once you have that, then you just expand it out and solve for R. Okay, but I'm expecting some questions now. Okay, so I'll just carry on filling in these numbers and you can ask me any questions if you have any. Okay, so 2.8 plus 0.4 R is equal to 2.63 plus 0.75 R. And if you get 0.175 equal to 0.35 R. Okay, and then you get R is equal to.
Someone is asking if the EMF is not 2.8.
No. Okay, let me answer that important question. This is what the voltmeter is reading. The 2.8 volts is what we're getting up here, okay? That's the 2.8. And when the switch is open or closed, that's the voltmeter reading there. The EMF is E there. Okay, so it's not. So the 2.8 is not the EMF, it's what the voltmeter reads. And see, it says here, the voltmeter reads 2.8 volts.
I'm sure that's clear. Thank you.
Okay. Okay, so I'm going to try and bring the screen down a bit. But what's important here is that you understand how to solve this type of problem when they've given you this information, how to solve it. And then it's important that you put the correct values in here for the resistance. See, in that case, it's 7, and here it's 3.5. Okay, so these are important concepts to know.
I think there's a question about numerical asking, was it okay to round off before the end of the question?
You can carry extra significant figures. It's better to carry some extra figures if you want to. Your final answer would be like 0.5 or 0.49. They would both be acceptable.
Thank you.
Okay. Because if you left the 2.62, whatever, 25 here, then you get 0.5. If you leave more digits here, but when you round it off, you get the 0.49. I did notice that when I was doing the calculations. Okay, so this here, if you are able to do this, you can get 8 marks. Okay. Okay, so that's the internal resistance. And I think you know what the next question is. Oops. The next question is calculate the EMF of the battery for 2 marks. Okay, so that's what we're trying to calculate. And when we calculate it now, you'll see that it's not 2.8. Okay, but let's do that. Calculate the EMF. I'm sure you can do it now before me. So EMF. The EMF is equal to I R plus R. And then you just choose any one, whichever of the 2 equations. You must get the same answer because it's the same battery, okay? So let's just use 0.4 for the current and the correct resistance, 0.49 for the internal resistance, and you get 2.996 volts. Okay, if you put some other values in there, you might just get an answer of 3 volts. But that's how you do it. Okay. Are there questions?
I think we can continue. There's no question yet.
Okay, so this is question 8, okay. Now, the next question that I want to do, someone had emailed this to me. Here. Okay, this is a question. I tried to write it out. A learner uses an electrical heater of resistance 48 ohms that operates at a potential difference of 240 volts to heat her room for half an hour. Calculate the cost of operating the heater if the cost of electricity is 1 Rand 47 per unit, and 1 unit is equal to 1 kilowatt hour. Okay, so once you've read the question, you know what they're asking us for now. They want us to find out, oh, how much is it going to cost to keep the heater on for half an hour? Okay, and the unit, one unit is 1 kilowatt hour. So let's just start by writing down, and I'll just change my pen to red. So we have that the resistance is equal to 48 ohm. We have that, I'm going to write here so you can still see the question. V is equal to 240 volts. And the time is equal to half an hour. And it's very tempting to write it as 30 times 60 seconds. And we also know that the cost is 1 Rand 47 per kilowatt hour. Okay, so for us to do this, we need to find out how much of energy is being used. Okay, so how much of energy is being used before we can calculate the cost. And to get the energy, we need to know what's the power of this apparatus that we are using. So we need to calculate the power. If we have the power, then we can multiply that by the time that it's on and get the energy. Once we have the energy in the correct unit, we can just multiply it by the cost or by the price, and then we will get the cost. Okay, so what's important is that you know that we are talking about kilowatt hours. Okay, so if you have R and you have V, you've got T, can you calculate the power? Okay, you can, and the easiest way is V squared over R. And that is just equal to 240 squared divided by 48. Okay, if you do that, you will get 1,200 watts. Okay, but we don't want it in watts, we want it in kilowatts. Okay, so you have to divide this by 1,000 divided by kilos. You're going to get 1.2 kilowatts. Okay, so that's the first step. We've got the power in kilowatts. So what is the energy? Okay, maybe again, I'm writing too many steps, but I think it'll help. It's power multiplied by time. Okay, so the power is 1.2. And I'm just going to put the unit in here, right? Kilowatts multiplied by the time. So what am I going to use for time? I'm going to use half an hour because I want the time to be in the unit of hour. So multiplied by 0.5 hours, because that's how long she had it on. So 1.2 multiplied by 0.5 is 0.6. And what is the unit? It's kilowatt multiplied by hour. It's kilowatt hour. So that's the energy that is being used up. And if you're going to pay 1 Rand 47 for 1 kilowatt hour, how much is this going to cost you? So then we just say that the cost is equal to the energy that is being used multiplied by the price of it. And so that's 0.6 multiplied by, and then now you can write it in cents or I left it as 1.47, so this is in rands. And then my answer becomes, and I'll leave it as rands here, because this is also, well, let me leave it like that. 0.882. So that is actually just 88.2 cents, just 88 cents. Okay, so that's how you do that. You don't have to write out all the steps, but this is the method. Okay, are you happy with that? Okay, so we can move on to another paper and try to do some questions that you asked me or something that we didn't cover in our previous section. Okay, so here's one. Okay, so question 3 from the 2019 paper. The sketch graph, oh, sorry. Okay. The sketch graph below shows the motion of a ball that is thrown vertically upwards from the balcony of a building. The ball takes 0.6 seconds to reach its highest point, after which it falls downwards past the balcony. So this dashed line here, past the balcony to the ground, ignore the effects of air friction. Okay, so let's just look at this graph. So on the x-axis, we have time. On the y-axis, we have the position. Okay, so the highest point is reached at time t equal to 0.6 seconds, which they told us, and you can see it from the graph. Okay, so the first question is, how high is the balcony above the ground? How high is the balcony above the ground? It's for 1 mark, and they just told us that the ball is thrown upwards from the balcony of a building. So if we look at the graph here, you can see that the graph is moving, so starts here at 10 meters, because the position is on the y-axis, which means that the balcony is 10 meters above the ground. Okay, so maybe I can just write it here. It's 10 meters. We can read that off the graph. Okay, the next question is, write down the numerical value of time t. So if we look at the graph, you can see that it starts here at 10 meters and it takes 0.6 seconds to reach the maximum height. And then it comes back again to the same height at 10 meters there. So what is t? If it took 0.6 seconds to reach the maximum height, then it's going to take another 0.6 seconds to come back again. So the numerical value of the time t is going to be 0.6 plus 0.6, which is just 1.2 seconds. Okay. Define the term projectile, so you know that it's an object where the only force acting on it is the force of gravity. Now they're asking you 3.4, calculate the initial velocity of the ball. Okay, so I'm going to remind you again, in these sections, there's more than one equation that you can use. And you can also have a choice of where you want to start from. You have a choice of which direction is positive and which direction is negative. You choose whichever you are comfortable with, but once you've made a choice, you must be consistent and stick with it. Okay, so let's do 3.4. Calculate the initial velocity of the ball.
Sorry, there's a student
Yes.
who's raising their hand here. I don't know if they can talk quickly, please. If they want to ask something, no, Pil, can you ask quickly? You can unmute yourself and ask a question quickly, please. And then she's quiet.
Okay.
Can you please
Oh,
sorry, I wanted to ask if, can you please explain 3.2? I had network problem.
Okay, no problem. For 3.2, it asked us to write down the numerical value of the time t. Okay, and so when you look at the graph, t is here, and the curve is at that point. So time t is when the, is it a ball? Yes, it's a ball. It's the ball that went up, reached the maximum at 0.6 seconds, and then it came all the way back down to the height that it started from at time t. So I'm saying if it took 0.66 seconds to go to the maximum from 10 meters to the maximum height, then to come from the maximum height back to 10 meters will take the same time. So it'll also be another 0.6 seconds. So the numerical value of the time is going to be (0.6 plus 0.6, which is equal to 1.2 seconds. Okay, that's how you get 1.2 seconds.
Thank you.
Pleasure. Okay, so now we are on to 3.4. Calculate the initial velocity of the ball. Okay, so let's do that. We'll continue here. Yeah, okay, it doesn't matter. 3.4. So I'm going to say that VF is equal to, okay, V final is equal to V initial plus A delta T. So I'm going to use the first part of the motion where the ball reaches the maximum height. So at the maximum height, what's the velocity? It's 0, is equal to the initial velocity plus, oh, and I must tell you that I'm taking upwards to be positive. So my acceleration is acceleration due to gravity is minus 9.8. And the time that it took to get to the maximum height is 0.6 seconds. Okay, so I'm trying to write 0.6. And then if you put that into your calculator, you will find that VI is equal to 5.88 meters per second. And it's positive, which means that it is upwards. But we already know that because it was thrown upwards. Okay, so that's the initial velocity. Okay, calculate the initial velocity. Now they want you to calculate the maximum height above the ground reached by the ball. Okay. Okay, so what is the maximum height that it reached? Again, there are different choices that you have. I'm just going to do the one that I like, or the one that I think is easiest. It's delta y is equal to initial velocity multiplied by the time plus a half a delta t. Okay. So we're going to use the first part of the motion from the time that the ball was thrown up until it reached its maximum height. Okay, so what is VI? We just calculated it to be 5.88. What is delta t? We know that it took 0.6 seconds to reach the maximum height, plus a half. A is going to be minus 9.8. Delta t is 0.6. Okay, so this is easy peasy. Put that into your calculator and you should get 1.764 meters. Okay, so what is 1.764 meters, the delta y? So let's go back to the drawing. What we've calculated now is this height here. Right. That distance there, that's what we calculated as delta y. Okay, but what did the question ask? It said, what is the, calculate the maximum height above the ground. So our answer is not complete because the maximum height above the ground is delta y plus this part here, which is 10 meters. Okay, so to complete our answer here, delta y is equal to that. So the maximum height is equal to 10 meters plus 1.764.
There's a student who's raising their hand. And
Yep.
this, sorry, just in your equation here in 3.5, please just check. I think you forgot to put a delta t squared at the end there. So
Okay.
Time, yeah, it's squared. Yes, thank you. Okay, someone will raise their hand. Can they answer? Can they ask the question quickly?
I was also just emphasizing that she forgot to delta t squared at the end of the equation.
Okay, thank
Okay.
you.
Sorry, thank you. Okay, so to find the maximum height, when you find your delta y, just add the height from which you were starting. Okay, so that's 3.5. What is the next question? Okay, calculate the magnitude of the final velocity of the ball when it reaches the ground. Okay, calculate the final velocity of the ball when it reaches the ground. So again, you'll have a few choices of where you want to start measuring from. So we'll just look at two quickly, right? So we're trying to find the final velocity when it reaches the ground. So that's 3.6. Okay, so the equation we're going to use is VF squared is equal to VI squared plus 2A delta Y. Okay, so let's look at the first case where we are talking about from the maximum height till it falls to the ground. Okay. Okay, so I'm looking at from maximum height downwards. So then into this equation, right? I'm going to write the equation again. So just putting it in the box there. Okay, so then we're going to get VF squared. We're trying to find VF. It's going to equal to, at the maximum height, what is the velocity? It's just 0 plus 2 minus 9.8 and delta y. If it's from the maximum height till the ground, then delta y is going to be 11.76. but is it going to be plus or minus if it's from the maximum height downwards? And I'm taking upwards to be positive, then this is also negative. Okay, and then if you do that, then you should get that your final velocity is 15.18 meters per second. Okay, so that's one way that you could have done it. And then the other way, and I'm going to say or, because you choose it, you're only going to do one calculation. We can try to calculate it from the balcony. So from when it first started, okay? So from the balcony. And we're using the same equation. So from the balcony upwards, the whole motion. So we're going to still have VF squared is equal to, but now what is VI? VI is what we calculated. It was 5.88, okay? Plus 2A is that. And now's the next part. What is the value for delta Y if I am measuring from the balcony? So I want to go quickly here to show you, right? In the first case that we did, we measured from here, from the maximum to the bottom here. And so the delta Y was the entire height here, the one that we calculated. Now, if we are starting at 10 and we are finishing here, then what is the delta Y? Can you see that it's only that distance there? And it's downwards there, so it's going to be minus 10 because I'm starting from here. See? So in here, I have to put minus 10. The negative sign because it's below where I started from. Okay. And if you put that into your calculator, you must get the same answer. That your, VF is equal to 15.18. Okay. I think you guys are happy with that. Okay, so you choose whichever one you prefer to work with. When you're putting in your values here, just be very careful what value you're using for delta Y. Okay, it could be that, or something else. Okay. Oh, sorry. Okay, so 3.7, draw a velocity versus time graph for the motion of the ball. Draw a velocity versus time graph for the motion. Indicate the following on your graph: initial velocity, final velocity, and the time taken to reach the maximum height. Okay, so velocity time graph for this, you should all be very happy. And like, yes, I know how to do this. Okay. Oops. 3.7. Okay, so it's a velocity time graph. So velocity there. And then we'll make this to go lower there. Okay, so that's time in seconds. Up here, it's going to be V in meters per second. Okay. Okay, and then we know it's going to be a straight line graph. So they wanted us to, let's quickly remind ourselves. They want us to show the initial velocity, the final velocity, and the time taken to reach the maximum height. Okay, so final velocity is 15.18 meters per second, and the initial velocity was 5.88. So when we're drawing this now, it should be, and then the time to reach the maximum is here at 0.6 seconds, because they asked us for that. So initially, when the ball is going up to its maximum height, it's moving upwards, so the velocity is positive. Okay, so the velocity is like that. So I need to label this point as 5.88 because that's my initial velocity. Then the velocity decreases, but they're all positive until it gets to 0.6. After it reaches the maximum height, then what happens? It starts coming downwards. So now the velocity is in the negative direction, so below the x-axis. And it keeps going, but now it must be a straight line. Okay. It must be a straight line, and the bottom part of the graph must be longer than the top part. And then if we bring the line across here, what value goes here on this y-axis? It's the minus 15.18. Okay, yeah, and even here, when we calculated this VF from here, it's supposed to be downwards, hey? Which should have a negative sign for both of them, because it's plus or minus. Okay? We should not have left that out, sorry. Okay, so if we look at the graph now, we've labeled time, velocity, it's a straight line. There's the time to reach the maximum height, the initial velocity, the final velocity. Yeah, that's right. Okay, so that answers question 3. Do you have any questions on that? Okay, let's move on to the next question. Okay. Okay, and then also just to remind you, see this, all of this carried 18 marks. Okay, let's look at question 4. But maybe we can just go through it a little quicker. So a delivery vehicle of mass 5,500 kgs moving at velocity v to the right collides head-on with the car of mass 2,000 kilograms moving at 30 meters per second in the opposite direction. Immediately after the collision, the car and the truck move at 10 meters per second and 6 meters per second, respectively, to the right. State the principle of conservation of linear momentum in words. Okay, you know, the total linear momentum in a closed system is conserved or remains constant. Okay, calculate the magnitude of the velocity of the delivery vehicle before the collision. Okay, so what is V? Okay, so we know how to do this. So this is question 4.1. Let's take to the right to be positive. Okay, so we solve this by saying the initial momentum must equal to the final momentum. And if we write out our equation, we're going to have mv initial for 1 plus mv initial for 2 must equal to mv final for 1 plus mv final for 2. Okay, so here we will have 5,500 times vi plus 2,000 times, now it's minus 30. Okay, so in these momentum equations, just be careful with the signs. And that's equal to 5,500 times 6 plus 2,000 times 10. Okay, and so we can put that into the calculator, and then you will get that the initial velocity was 20.55 meters per second. Okay, so that's how we calculate the initial velocity. Okay, 4.3.
Sorry, Ashila, I think you're muted by mistake.
Okay, sorry. Okay, so if the collision lasts 0.2 seconds, calculate the force the car exerts on the delivery vehicle during the collision. So I'm just saying, while we got the drawing here, if you have a look at the car, you can see which direction the car is moving in. So you know in which direction the force that the car exerts on the delivery vehicle will be. Okay, so the collision is going to last 0.2 seconds. Calculate the force. Okay, so let's do that quickly. So for 4.3, we know the equation is that the net force multiplied by delta T is equal to the change in momentum, mvf minus mvi. Okay, so we can rewrite that as the net force multiplied by 0.2 seconds is equal to 2,000 multiplied by 10 minus 2,000 multiplied by minus 30. Okay, and if you put those values in there, then you're going to get that the net force is equal to 400,000 newtons. And then what is the direction of this? What is the direction of the force that the car exerts? On there, the direction is to the left. Okay, that is important. Okay, so that's question 4. Don't know if you have any questions. Okay, let's try to answer one more at least. So, okay, let's look at this type of question. Question 5. A 4 kg box is held stationary at point P, so it's not moving. The top of the plane, PQR, inclined at an angle to the horizontal. the portion PQ of the plane is smooth, while the portion QR is rough. Okay, and then they've given us all the dimensions for the height, or the heights. State the principle of conservation of mechanical energy in words. So same thing, the total mechanical energy in a closed system remains constant, always conserved. Okay, so determine the speed of the box at position Q. Okay, so they told us at the top here at P, it is held stationary. We know that it's 3 meters above the ground, or it's 1.7 meters above Q. And we want to know when it gets to Q, position Q, what is the speed? Okay, so how are we going to do that? We're just going to use the conservation of mechanical energy. Okay, so let's do that. Okay, so 5.1. We're going to write it as, I'm writing it as E. So the total mechanical energy at P is equal to total mechanical energy at Q. Okay, and what is the total mechanical energy at P? That's going to be the potential energy plus the kinetic energy. So let's just write out the equation. So it's going to be mgh plus a half mv squared. All of this is at point P, right? That must be equal to mgh plus a half mv squared at Q. So I'm saying the total mechanical energy at point P is equal to the total mechanical energy at Q. Okay, so at point P, what is mgh? Okay, so we know that m is 4 kgs, g is 9.8, and h is 3 meters. Okay, now I'm just going to show you that again. And then plus a half. Now, what is the kinetic energy here at point P if it's held stationary? Okay, so V is 0, so the kinetic energy is 0. So it's plus a half of 0 squared. Okay, so that's all on this side. And then that must equal to mgh at Q. So it's 4, G is 9.8, and H is, what is H? So when we measured P to be 3 meters, we measured it relative to the ground. So this is 0 meters. Okay, so if P was 3 meters, then Q is going to be 1.25 and not 1.75. Okay, so it's 1.25 plus a half, M is 4, and V is what we're trying to find. Okay, so if you do all of this, 117.6 minus 49, and you'll get that V is equal to 5.86 meters per second. Okay, that is, we calculated this, just to remind you, using this as our 0. Okay, if you wanted to, you could choose this point to be 0 meters, then H for P would be 1.75, and H for Q would just be 0. Okay, so you can choose where you want to choose where the 0 of your potential is. Okay. So that answers 5.2, which says determine the speed of the box at point Q. Okay, so 5.3 says the box experiences a kinetic frictional force of 15 newtons as it moves with a constant velocity from Q to R down the plane. Okay, so when it's traveling from Q to R, the kinetic frictional force is 15 newtons as it moves with a constant velocity. Okay, so state the work energy theorem in words. Work energy theorem, that's just that the total work done on an object is equal to the change in the object's kinetic energy. Okay, but you know that. Okay, so 5.3.2, draw a labeled free body diagram showing all forces acting on the box as it moves from Q to R. Okay, so the box is, the box is here at Q and it's sliding down to R. What are the forces that are acting on it? Okay, it's resting on the surface, so we know it's going to have a normal force. It's going to have its weight acting vertically downwards. And it's a rough surface, so there's going to be the frictional force acting up the plane. Okay, so draw the free body diagram, 5.3.2. Okay, 5.3.2. Okay, so I'm going to draw that for the box. Then I'm going to draw the line that's always vertically down. Okay, you can call it the weight, or we call it mg. Then there is a force that is parallel to the surface, but in the opposite direction that it's sliding, which is the frictional force. And then there is a force that is 90 degrees there, 90 degrees to the surface, which is the normal force. Okay, so that is my free body diagram. Okay, when you have the free body diagram, now they want to ask us another question. Okay. Use the energy principles to calculate the distance x between Q and R. Okay, between Q and R, what is the distance x? Okay, so if we use energy principles, so they asked us about the work energy theorem. So the work done is the change in the kinetic energy. So it's moving at a constant velocity, which means the change in kinetic energy is 0. So we're just going to use the work energy theorem. Okay, so let's find the distance x between Q and R. Okay. So we always start by writing out our equation, right? And the equation is that the network is equal to the change in the kinetic energy. Because the speed's not changing, the network is equal to 0. Okay, so what's doing work on this box? Our free body diagram shows us there's a frictional force and there's the gravitational force. So it's only the weight and the frictional force. So those are the two. So it is the work done by friction plus the work done by gravity is equal to 0. And once you've got that, then you can do the rest. So the work done by friction now is the frictional force times the displacement x that we are trying to find Let me write it as a, what? Okay, I'm just going to write it like this. F times X cos of 180 degrees, or cos of theta. Let's just not leave out the steps here. Cos of theta plus here, it's just going to be the work done by gravity, which is just going to be mgh. Okay, or mgh cos of 0 if you want to, and that's equal to 0. So let's put in the values. The frictional force they told us is 15. Okay. And this X cos of 180 degrees, this is the X like that they are asking us to calculate, okay? It's not a multiplication sign, that's the X. And this is cos of 180 degrees plus the mass is 4, G is 9.8, and the height that it falls from Q to R is 1.25 meters. And if you solve that, then you'll get that X is equal to 3.267 meters, or 3.27 meters. Okay, so the part that was important here is work energy theorem. And they said constant speed, which meant that there's no change in the kinetic energy. V initial and V final are exactly the same. Okay, and then for 1 mark, the angle between the incline and the horizontal is now increased. How will this increase affect the coefficient of kinetic friction of the box? Just write only increase, decrease, or remain the same. So what do you think? The angle is increased. So if they make this steeper, will that affect the coefficient of kinetic friction? Does that depend on the slope? Or is it just depending on what the surfaces are? Okay, it just depends on what the surface is. So increase, no. Decrease, no. Remain the same, yes. So the correct answer is remain the same. Okay, the coefficient of kinetic friction does not depend on the incline. Okay, so that's question 5. Do you want to ask any questions? Because we have a few minutes. We could maybe do some MCQs or something, if you have any questions. Anything you want me to explain? Okay, do we have questions?
I think there is a question here, but I don't know if we can do that. Someone is asking, can you please help us with the optical phenomena and properties of material? Not sure what exactly would they mean by that. And someone is saying, can we do question 6 quickly? I think there's a question. Question 6.
Doppler effect. Okay. Okay. Well, we did it.
It's a
Okay.
short question. I'm not sure if you did it now, but
No, we didn't do it now. We did a Doppler question previously, but we can have a look at it now if you want. Oh,
yes.
okay. Yeah, okay, let's do that then.
I'm not sure about the other one there. That one is asking about optical phenomena and properties of material. I don't know if we can do that right now with time. And I'm not sure what they mean exactly by that.
I'm not sure what that question is asking.
Actually, I think it's a Doppler effect, actually, that optical phenomena, that would be a Doppler effect. Properties of material, I think that's a photoelectric effect, if I'm not mistaken.
Okay.
I don't know if you can do that right now with time, though.
Okay, let's look at, we can look quickly at Doppler effect, and then we can see if there's a question here on photoelectric effect, and we can also have a look at that.
Okay, thank you.
Okay, so here's one now. An ambulance with its siren on moves at constant velocity. Oh, sorry. Moves with a constant velocity towards a person standing next to the road. Okay, let's get my pen here. Okay, so it's moving towards a person standing next to the road. The person measures a frequency which is 110% of the frequency of the sound emitted by the siren of the ambulance. Name and state the phenomenon observed above. Okay, so the phenomenon is the Doppler effect, and then they're asking you to state what the Doppler effect is. You know that it's the change in frequency detected when there's a difference in the velocities between the source and the listener. Okay. If the speed of sound in air is 340 meters per second, calculate the speed of the ambulance. Okay, so they want us to calculate the speed of the source. So it's okay, let's do that. And then how will the frequency, the next question is, how will the frequency measured by the person be affected if the speed of the ambulance is increased? Okay, right, only increase, decrease, or remain the same. Okay, so we know if the speed's increasing, then we go, the frequency is going to increase. But let's answer 6.2 quickly. Calculate the speed of the ambulance. 6.2. Okay, so we have to start by writing out the equation. Times the frequency of the source. Okay, let me just quickly see this. A person standing next to the road. Okay, so the person, so the listener is standing next to the road. The person's not moving, right? And ambulance is coming towards the person. So if the person is standing still, then that's going to be 0. Okay, the ambulance is coming towards the listener. So this is going to be minus. Okay, and then we know that they told us that this V is 340, but they also told us, instead of giving us values, they said a person measures the frequency, which is 110% of the frequency of the sound emitted by the siren. So we write that out as 110 over 100 of that. Okay, it's 110% of the frequency is equal to, and this is 340 over 340 minus Vs is what we're trying to find, times Fs. Okay, so the part that may have caused you some problems would be this bit here, where they didn't just give you a value for the frequency, that they hear, but they told you it's 110% of the frequency of the source. Okay, so that's how we write that out. So this will cancel with that. And then if you put that into your calculator, you can find Vs. Okay, and you should get 30.91 meters per second. And then just to answer the question, they said if the speed was increasing, then what would happen? And the answer would be just increase if you had to choose between those two. Okay, I went a little bit fast, but I think that this part here, this is where the part that's different from the other questions. It's the 110%. 110% of the frequency of the sound emitted by the siren. Okay, the person measures a frequency which is 110% of the frequency of the sound emitted by the siren. Okay, is that okay?
Yes, I think that's great. Say thank you.
Okay, and that has brought us to the end of our time. I'm just trying to see if I can, maybe we can just quickly look at the photoelectric effect. Should we try to quickly, maybe we don't have to write out all the solutions, but we could just discuss
Yeah,
it.
I'm sure you just give ideas as well. Yes, thank you.
Yeah, okay. Here's a question on that, right? Okay, so a learner investigates the relationship between the maximum kinetic energy of photoelectrons and the frequency of light when light is incident on a metal surface of a photocell. The graph obtained by the learner was found to cut the x-axis at f0 equal to 5 times 10 to the 14 hertz. Okay. Okay, so is the electron on which the light is incident the cathode or the anode of the photocell? Okay, we know that it's the cathode. Okay, the light falls onto the cathode. Write down the name of the physical quantity represented by F0. Oh, sorry. So what is F0? Okay, you all know what that is. It's the threshold frequency. Okay, but I'm gonna write it here. I think you know this. It's the threshold frequency. Define the term work function. Okay, it's the minimum energy that an electron in a metal needs to free itself from the metal surface. Okay, and then calculate the work function of the metal. Okay, so the way we'll do that, the work function is equal to h f0. Okay, so h is Planck's constant. You know that value. It's 6.63 times 10 to the minus 34. You'll get it from your table. And f0 is what they've told us here. Here it is, 5 times 10 to the 14. Here's f0. So then you just go and put that into this equation. The Planck's constant from your table and the frequency here, threshold frequency, and you will get the work function. Okay. And then the next one, it says calculate the frequency F1 shown on the graph. Okay, so we've got the threshold frequency, and now they want us to calculate F1. And what they've given us in this graph is the kinetic energy. Okay, so just to remind you quickly that you have light of some energy coming into here, and then you have your electrons here or your photons here, and then they absorb some energy, the work function to bring it there to the surface, and then the extra energy is kinetic energy. Okay, so now they've given us the kinetic energy and we've calculated the work function already. So then you can calculate F1. Okay. I don't know if that helps. Maybe I'll just write that solution for you. We'll just do 10.4 and 10.5 quickly. Okay. Oops. Okay, so 10.4, we said that the work function is equal to h times the threshold frequency. And then that is 6.63 times 10 to the minus 34 and 5 times 10 to the 14. Okay, if we do that, we should get 3.32 times 10 to the minus 19 joules. Okay, that's the work function. Now for the next part, for 10.5, we're trying to find F1, and they've given us the kinetic energy. So the equation we'll use is the energy that's coming in, HF, is equal to the work function plus the kinetic energy. Okay, so I'm not sure what your equation is, but it's the kinetic energy. Okay. So HF is 6.63 times 10 to the minus 34. And we're trying to find this F1. That is equal to the work function. We'll just get it from there. 3.32 times 10 to the minus 19 plus this value for kinetic energy is 11 times 10 to the minus 19, okay, from the graph. 11 times 10 to the minus 19. Okay, so what I wanted to tell you quickly is maybe this is more important. That you get from your graph, and this is from there. You calculated it already. Okay, so if we've got all these values now, you can just solve for F1. And then you should get 2.15 times 10 to the 15 hertz. Okay. Okay, I hope I didn't speak too fast. But that's how you'd solve it. Okay.
Yeah,
So that's
sure.
it from my side.
Yeah.
Okay, are there any other questions they want to ask quickly? Not any more calculations?
Comment saying thank you.
A pleasure. Let me please use this opportunity to wish you all the best of luck for tomorrow's paper. Just be calm and you can do this. You've got this. So good luck, good luck, good luck.
Ashila,
Yes.
Good luck.
I think there was one question. I think you did the Doppler effect previously.
Yes. Yes.
Somebody wanted you to go over the second to last step.
In the previous thing that we did.
Yeah.
The previous
Doppler
paper
question.
or today's one?
The question you did before this.
Oh, okay. So here. Okay. Well, what's the question?
They want you to go over well, I guess it's the second step. The second to
Oh,
last
this
step.
110%. Okay. Okay. Let me just explain this thing again. Okay. So let's look at Just question 6. Okay, so just to remind you now, the Doppler effect is where you have a source and it has a certain frequency. But when the source is moving relative to somebody who's listening to it, an observer or a listener, then the listener hears a different frequency. Okay, and that is the Doppler effect. In this case, you have a person who is standing next to the road. So the observer or the listener is stationary. And the ambulance, which has a siren on, so that's the source is coming towards the person. So we know if the source is approaching the listener, the frequency is going to be larger or higher than the frequency of the source. Now they tell us that the person measures a frequency which is 110% of the frequency of the sound emitted by the siren. Okay, so this part, frequency of the sound emitted by the siren, that is frequency of the source. Okay, so what the person measures is a frequency that is 110% of that frequency. And they want us now, if they told us that the speed of sound is 340 meters per second, what is the speed of your source? What is the speed of the ambulance? Okay, so when we do that, we go to the equation that we know. Okay, so this is the equation for Doppler effect. Okay, this equation here. Now, we knew that the person, the listener was not moving. So we said this velocity is 0, or that speed is 0. So we've only got the speed of sound in air, v, on the top. For the bottom, we have the speed of the source. We know that the source is approaching the listener. So the frequency we're going to get is going to be larger. So this denominator here must be small. So this is a negative sign. And then the rest of the equation is the frequency the listener hears is equal to V divided by V minus Vs times the frequency of the source. So now we can rewrite that, putting in the values for the speed of sound in air, 340 meters per second. We're trying to solve for Vs. What is the frequency that the listener hears? The listener hears 110%. So 110 out of 100 times the frequency of the source. So that's how I get that value for frequency of the listener. On this side, I still have frequency of the source. So I can divide by frequency of the source on both sides of my equation. So that goes away. And then I will just have the numbers. So the only unknown is Vs. So I can solve for Vs. Okay, I hope that was better.
Miss,
Yes.
can I please ask how can you approach the multiple choice questions?
I don't know. What do you mean?
How can you approach them?
Oh, okay. So are you asking me, like, when you're reading through all of them, how should you do it? Because
Yes,
each
the
question
multiple
is
choice.
different. Okay, so if you want some advice on that, so when you're reading through it, I advise you to read the question first, okay? Read
Yes,
the
ma'am.
question and block all the answers. So you cannot see what the answers are. So let's just go to, I'm just going to show you as an example, just the first question here, right? Let's just look at the first question only. Okay, so if you can see here, it's 1.1. It says, okay, it's easy, okay, never mind. It says the force or the component of a force which a surface exerts on an object with which it is in contact and which is perpendicular to the surface is called the. So you read that question and do not look at the answers. You cover all the answers. You read the question and you find your answer. So what is it? Without looking at this, the force or component of a force which a surface exerts on an object with which it is in contact and which is perpendicular to the surface is called the, what force is that? That's perpendicular to the surface. We know that it is the normal force. So then you uncover all the answers and you look for normal force. And if normal force is there, you know, that's the right one. Okay, so that's how I advise you to do that type of question. And then if you're looking at the next one here, it tells you that the satellite experiences a gravitational force of magnitude F on the surface of the Earth. The radius of the Earth is R. Now it circles the Earth at an unknown height above the surface and experiences a gravitational force of magnitude a quarter F. This unknown height above the surface of the Earth is, so you cannot guess that. You have to go and take your equation for the gravitational force and work it out. And then when you get your answer, look in your A, B, C, D, which is the correct one. Okay, that's how you do the multiple choice. Whenever they ask you something, you have to write it out. Okay, I said one, but let's do the last one on this page. Which one of the following is the unit of measurement for the rate of change of momentum? So I don't even look at those answers, right? Rate of change of momentum. So I write change of momentum, rate of change of momentum. That means delta P over delta T. So how do we find delta P? It's the change in mv. Okay, so it's delta mv, but I'll leave out the deltas now. So it's mv over T. What is the unit for mass? It's just kilograms. V is meters per second, and time is second. So then I end up with kilogram meter, and I've got second squared at the bottom. And so when I look at that, what is kilogram meter per second? Kilogram is just a mass, and meters per second squared is the unit for acceleration. So ma, what is equal to ma? Just the force. So what's the unit for force? And if I go look at my answers here, watt, kilogram, ohm, newton. Oh, okay, that's the answer. Okay, so that's how I would advise you to go through your multiple choice questions.
Okay, I think we're done, Ashna.
Okay, thank you, everyone.
Okay, thank you. Thank you so much.
Thank you. Thank you.
Part of the UKZN experience is the opportunity to be part of a community and to network with not only our world-renowned academics, but with future game changers and leaders. They do say that the extent of one's success can be attributed to those they rub shoulders with. Therefore, you must surround yourself with like-minded people. So, how do you become part of a community that is committed to your self-development? How do you become part of UKZN? First, you have to apply.
All applications for undergraduate studies at UKZN are processed through the Central Applications Office, CAO. This is for both your course and student residence application. The application process is as follows. Step 1. Consult the CAO Handbook. This handbook provides a list of all qualifications available at UKZN. Step 2. Have a look through the various courses offered and choose a program that interests you and for which you meet the minimum requirements. As one of the top 5 universities in the country, UKZN promotes academic excellence. So meeting the minimum requirements does not guarantee you a place to study. Step 3. Find the program code linked to your chosen qualification. This is the code you need to enter in your application form. Okay, let me show you something. You see, a code has 3 parts. Example, for BCom in accounting, the code is KN-P-BCN or KN-W-BCN. Crazy code, right? Well, basically, the KN stands for UKZN, the middle part stands for the campus of your choice, P for Pietermaritzburg, W for Westville. Then BCN stands for the actual course. Make sure to get these codes right. Step 4. Use this program code when completing your CAO form, which is available from the CAO website. Your application will be sent to UKZN. You can always check the status of your application using your CAO number, ID number, or passport number on this website, www.caocheck.ukzn.ac.za. For more information, visit www.cao.ac.za.
It's that easy. Pay close attention to closing dates for qualifications. For example, MBCHB closes on the 30th of June, whilst other undergraduate programs close on the 30th of September. What are you waiting for? Apply now and shape your future today.